So we have the pleasure to hear Blekherman from Algebraic. We'll talk about extremal combinatorics and real algebraic geometry.
Thank you. So yeah, I'm very happy to be here. It's been a long time since I was in Europe, and this is a workshop for there's a lot of young people. So I thought I would give you an experience from my own time as a graduate student. And at that time it was sort of right before Beamer and and LaTeX became popular. So what happened was people used to make handwritten transparencies, right, that they would put on the projector. And I also did that a bunch of times. So this time I'm going to give you handwritten slides. It's not quite, I didn't make transparencies, and I don't know if overhead projectors still exist, right? That would put the organizers through a lot of trouble. But anyway, perhaps it will be a disaster, but we will see. But as one of the as one of the consequences, please move closer. Don't sit at the back. Okay. So, right, so I want to talk about some extremal combinatorics problems, and but I think the reason that I want to talk about them here is I think there are actually going to be a lot of connections to polynomials, and I don't know, some things that I hopefully you will find interesting. But first, I need to sort of give you a bunch of definitions. So I think we have plenty of time, so I'm not in a rush. So if you have questions, please feel free to ask questions and interrupt me. There's not a problem this time, I hope. Okay. So right. So I'm going to talk about graph homomorphisms, and so in a way, what are the sort of problems that we want to talk about? Is how many times does a graph contain a certain subgraph? But now you need to talk about what does it mean to contain a certain subgraph? So there is one notion is kind of easy. You just look at how many times a certain subgraph is contained in the graph, and you just let's say you want to count triangles, then you just count the number of triangles in your graph. So you look at all three vertex subsets and you count the triangles. But there is a slightly different notion of how do you count number of copies of a certain subgraph, and that goes under the name of graph homomorphisms. So what is a graph homomorphism from a graph G to H? It's a map from vertices of G to vertices of H such that it preserves adjacency, right? So that if your two vertices were connected in G, then the images must be connected in H. In particular, because the graphs that we're working with are going to be assumed simple, so they will not have any loops. They will not have multiple edges, but because you don't have loops, two vertices that are connected in G cannot be mapped to the same vertex of H, right? Because if you preserve adjacency, that would need to create a loop. Okay, and now by comp from G to H with a capital H, I'm going to denote just the number. So that's how I'm going to count the number of copies of G in H. And okay, so let's do a certain like an example. So what is the number of homomorphisms from this cherry to an edge? So basically, there are only two. What are the two? I can decide to map these two vertices to the bottom vertex and then the top like this, or I can map them like that, right? And that's it. So these are the two possible homomorphisms from the cherry to an edge. And now, what about the number of homomorphisms from a triangle to this graph? Well, you see, because adjacency must be preserved, the triangle on the left must be mapped to the top of this triangle here. But now there's 6 different ways of doing that, right? Because I can basically kind of defines a permutation. These 3 vertices must go to these 3 vertices, but I can do it in 3 factorial, which is 6 different ways. Okay. Any questions or concerns? Okay, so that's the notion of homomorphism. Let's see. Okay, great. And now there's a notion of homomorphism density. So what is this? Again, intuitively, what does this mean? It just says this is the probability that the random map So now I can create any map from the vertices of G to the vertices of H. It's the probability that this map is a homomorphism. So what is this? So this is the total number of homomorphisms from G to H divided by the total number of maps between the vertices of G and vertices of H. And so what does this mean? So well, it's the number of homomorphisms. Now, how many maps are there? Well, for every vertex of H, I have the number of vertices of G many choices, right? Because now I can make any map. And so this means that I must, I'm going to make vertex of H, the size of the vertices of H many choices, and I'm going to, and the number of choices is the size of the vertex of G, right? So that's the homomorphism density. Again, it's the probability that a map between that a map between two graphs actually gives me a homomorphism. Okay. All right. So far, these are just combinatorial definitions, right? There is no hint of polynomials. But now, hopefully, we will get to something that will sound familiar. So now, what are we going to try to understand? We're going to try to understand inequalities in homomorphism densities that are valid for all target graphs H. So basically, what I want to do is what kind of inequalities? Well, I'm going to write some polynomial inequalities in homomorphism densities that are valid for all target graphs. So let me give you an example. This is a valid inequality. So this is cherry minus h squared is greater than or equal to 0. Now, how to read this, right? What is the meaning of this? So in fact, we're going to hopefully prove this inequality later in the talk. Okay, might not be obvious why this is true, but this is not hard to prove. So what does it say? It says that how do you read this? So this is like my shorthand notation. So what this really means is that the homomorphism density from cherry to any graph H minus the homomorphism density from H to any graph H squared is greater than or equal to 0. Okay, so in general, I can write down sort of inequality. I can write down kind of expressions like this that are going to be polynomial expressions in homomorphism densities. Right, and what I want to know is, I want to find out all of the expressions that are non-negative for any target graph H. Those are the things that I would like to understand. So, I mean, hopefully now there's at least, I don't know, some smell of real algebraic geometry, maybe not, because we're talking about non-negativity, right? Although, usually we talk about non-negativity, and then they're still kind of like polynomials, right? But the things that, but evaluation is not evaluation on points, right? Evaluation is evaluation on graphs. Okay. Questions? We're good? Okay. Okay, and so there's a fundamental result in this area that says that basically deciding whether a given inequality is valid or not is a hard problem. So what does it mean to be a hard problem? Actually, it's a very hard problem because it is an undecidable problem, right? So what does it mean? Essentially, it says that there is no algorithm that can correctly tell you whether a given inequality is correct or not. So given an inequality, there is no algorithm that is going to output correctly yes or no, right? So if it's valid, if the inequality holds all the time, then it's going to output yes. If it doesn't hold, it's going to output no. And now, what is from the algorithmic point of view, what is the difficulty here? So the difficulty lies with the yes answer. Because if this is not, if the inequality is not valid, it must be invalid on some graph, right? There must be less than 0 on some graph, and you could just enumerate graphs and ask a Turing machine to go through them, one by one. And if the answer is no, it is going to find it. right? And then, you can run a separate Turing machine for the yes, and then, you can have some tricks, you can combine another, basically you can have a couple of algorithms, and then you can link them together if you don't like the words Turing machine, right? So you can have a couple of algorithms, there is a yes algorithm, there is no algorithm, and you could combine them, but the issue is that you don't know how to do the yes part. So if you want, go into real algebraic geometry language, right? What is the issue here is with certifying non-negativity. Right. So the issue is that there is, what this theorem says that there is no good enough certificate of non-negativity. Although, as we will see later in the talk, in the second half of the talk, there is a notion of a sum of squares calculus here in this setup. So you can prove things kind of using, let's say, semi-definite optimization. And there is even a nice positive Stellensatz that I want to mention. So it is due to Lovas and Segedi, but kind of improved by Netzer and Tom. And so basically what it says is, like standard positive Stellensatz, it says that if you have an expression that is valid, so you have an inequality that is valid, if you add an epsilon to it, any epsilon, then you can certify it via sums of squares. Right? So this is kind of it's kind of an interesting thing that's happening here. Is that, if you're allowed to add an epsilon, then there is an algorithm, right? But if you're not allowed to add an epsilon, then the problem is undecidable. So it's as hard as, it's not possible to do it with an algorithm. And I want to present sort of a different perspective on this result that has a lot to do with polynomials. And in fact, also the original proof has something to do with polynomials, but I will make some comments on this later. Okay, any questions?
Certificate here, you mean someone?
No, well, so you see, this undecidability says that there is no reasonable certificate, even beyond sum of squares, right? It just says that, there is no algorithm. If you could certify it via sum of squares, then you would have an underlying algorithm, and then the thing would be decidable. Right. So in particular, you can also define a notion of, let's say, sum of squares of rational functions that you're familiar with from real algebraic geometry. Maybe it's not quite clear, first of all, what sum of squares is here, but I will define that. But it's also not clear what sum of squares of rational function is. But it doesn't matter. Anything that leads to a reasonable algorithm is impossible. Right. It doesn't matter how you want it to certify it. If you wanted to define a notion that is kind of equivalent to sunk polynomials, right? Anything that leads to any certificate that leads to an algorithm cannot work. That's what the undecidability result says.
There maybe a type of G is H or the last G?
Oh, yes. Thank you for reading ahead, Giorgio. Yes, that is correct. There is a typo, yes. Yeah. No, we'll see that actually very low degree. I mean, first, we need to understand what is the notion of degree. But yes, you can write down very simple inequalities. Let's put it this way: that somehow will be hard for sum of squares to certify. I mean, of course, given if I don't specify what is my method of certification, then of course, I can always certify any inequality because I can assume that my algorithm knows it. Right, but it somehow eventually says that there is no algorithm. Yeah.
The psychometrics, is there an algorithm that is better than extremal?
No, well, I mean, I'm not sure because if as long as the graph is fixed, right? In principle, one could say that you should just find out what the right answer is, and you should output that, right? I mean, of course, how do you find out what the answer is? But from an algorithmic point of view, if you limit yourself to the size of graph, there should be an algorithm because for everyone there is the right answer, yes or no, and that's what and you can just hard code your algorithm to output that. But in principle, there are many different ways of proving these inequalities, right? So I will only focus on one, which I will call sum of squares. But in there are many, but they're just combinatorial tricks. of proving that some inequality. In some sense, the sum of squares is also some sort of combinatorial trick combined with squares. Okay. Sorry, any other questions? Okay, so yeah, so why should this problem be hard? So I think that there's some, one can embed some polynomial problems in this framework. So consider even cycles. So what does it mean? It's a cycle on an even number of vertices. And here by C2, I will mean an edge, not like 2 copies, because I don't allow myself that, but that's an edge. And so now it is kind of it's a simple exercise in combinatorics to prove that the number of homomorphisms from, in fact, any cycle to a graph H is just the trace of A to the K, where A is the adjacency matrix of the graph. So what is the adjacency matrix? You put 1 where there is an edge, it's a symmetric matrix. You put 1 where there is an edge between I and J. You put 0 when there is not an edge between I and J, in particular because our graphs have no self-edges. On the diagonal, you will see zeros, and then you will see 1s for edges. And of course, the trace of A to the K is, now there is some linear algebra, is the sum of K powers of eigenvalues of the matrix. Okay, so I'm going to do even powers because that's going to make things much easier, because in the end, I'm going to adopt adding non-negative numbers, right? And that makes things much simpler. Okay, so now what we're going to do, so I'm going to really focus on just the cycles, or later we will see how to do things maybe a little bit farther than the cycles, but for now, let's just try to understand what happens with the cycles. Okay. And there is already some polynomial here, a very simple one, symmetric one, which is the sum of K, 2K powers of eigenvalues. Okay. Any questions? It's okay. Okay, so now here is the thing that I want to record. So now, for any graph H, I want to produce a point in the plane. So a point with only 2 coordinates, right? So what am I going to record? I'm going to record the homomorphism number of C4, so the 4 cycle to H divided by the 2 cycle, which is just H squared. Then homomorphism number from C6 divided by C2 cubed. And if you think about it, if I switch this big H to the little h, nothing is going to change, because in the end, what is little h, the homomorphism density? It is the homomorphism number divided by something at the bottom. And somehow the bottom, I set things up so that the bottoms of these 2 fractions are going to be the same. You can check that. It's not, it's not super important. I mean, it is important in the end, but it's not super important to see the calculation right now. So basically what I want to say is that, big H, little h is not going to make a difference, right? So what am I going to do? So it's the same as saying now that I record the 4th powers of eigenvalues of the adjacency matrix divided by the sum of the eigenvalues squared, and then the 6th power divided by the sum of squares. Okay, so for every graph, I'm just going to produce a point in the plane. And what we want to understand is, what is the set that we're going to produce in the plane? Or really, because here, okay, well, maybe the eigenvalues is not clear, but if you look at this expression, you can see that these are all rational points, right? So in the end, I'm going to produce a bunch of rational points that's not so nice, and we want to understand what is the closure of the set, right? Okay, so this is the object of interest, right? And then I will explain, how is it relevant to our problem. So again, for every graph H, I'm going to record this number, which is the number. Basically, you can think about the number of 4 cycles, if you count them properly, divided by the number of edges squared, and then 6 cycles divided by number of edges cubed. Okay, any questions? Okay, so now let's forget it now. Now let's forget about graphs for a moment, right? Let's skip graphs and let's just go to polynomials, which are hopefully things that we like. I don't want to say we like more. Maybe that's maybe that's not fair, but right. But at least let's go to the things that hopefully we like. Okay, so let's forget. So basically, now let's forget about the fact that these things come. These are some maybe special numbers you could say because they're eigenvalues of adjacency matrices of graphs, right? So maybe there is some relationship that we might need to care about, but let's forget about that. Let's forget about that and let's think of these lambda i's as coming independently to us, right? So now they can be anything, right? So and also it is easier, because here I'm always working with squares and so on. Let's make a substitution. So xi is equal to lambda I squared, and now I'm just going to think of xi's as just some variables that have to be non-negative, right? That's it. Okay, now I've set all of this up. I said, we're going to do things in graph theory, and now I'm kind of taking all of the graph theory away for a second, right? All of this I'm taking away. And another thing to notice is that, basically what I'm doing here, this is polynomial of degree 4 divided by polynomial of degree 4. That's one of the reasons why I, normalized it like this. It's a polynomial of degree 6 divided by polynomial of degree 6. Or if you want, now these are polynomials of degree 2 and 3 respectively, my new variables xi. And this means that really, it's enough for me to understand what happens if I record these numbers for basically for the probability simplex, right? Where the sum of the xi's is equal to 1. I can renormalize everything, right? Because these things are homogeneous. Okay, and I'm going to introduce this new notation. This is just the power of some polynomial. Pk is the sum of xi to the k. And one more thing to remember is what we're doing here is one piece of graph theory will remain is that the graphs, I can evaluate my expressions on graphs with any number of vertices, right? So which means that here I can have any number of variables xi, because remember, the number of variables is the number of vertices, is the number of eigenvalues. So somehow what I'm doing is I'm recording these expressions, these simple power sum expressions, but I'm recording them for polynomials, in fact, these nice symmetric polynomials, because they're all power sums, in any number of variables. Okay, let me pause here. Any questions? Yeah.
How much you lose when you throw away graphs and consider all the...
Well, the bottom line is that we don't lose anything. So somehow recording this for arbitrary xi's and just reporting them for graphs will not make a difference. But maybe that's not obvious. Yeah. Well, they give me these nice polynomials. That's the thing. They give me these nice polynomials, and that gives me a way of understanding what happens to this map, in the polynomial world. When I forget about graphs, so I forget about the fact that these are eigenvalues, of adjacency matrices. More questions? Okay. So now, yeah, as I said, let's throw away all of the graph theory and let's look at the following map. So I map, basically I map the probability simplex. So this is the sum of the xi is equal to 1. I map it to R2 by just, because now the sum of the xi is equal to 1, which remember was the sum of lambda I squared, right? I can forget about the bottom, right? Now I don't even have a fraction, right? I just have a polynomial map. Right, so I just take my probability simplex and I map it by a simple polynomial map that just records the sum of second powers and the sum of third powers. Right, so this is a nice map. I do it for any, but the thing is that I do it for any number of variables. So you can see that the thing that we want is we want the image of this map as n goes to infinity. And okay, you could say, all right, but you have sets in the plane, but you're taking a limit of sets. Maybe that's complicated. The thing is that these are kind of nested increasing sets, right? Why? Because, because basically, if I plug in a bunch of coordinates equal to 0, I get probability simplex and fewer variables. So giving myself more variables is only going to potentially increase the image. So what I have is a nested increasing sequence of sets. And in that case, it's no problem to take the limit, right? I just take the union and I take the closure. Right, and this is the thing that we did because this is a formal workshop, and I think Cordian is a participant. And I think maybe Sebastian is going to maybe actually speak even potentially even maybe exactly about these things later in the workshop. He's one of the Poema supporters, and also with my students for the Okay, but any questions right now? Do you understand the setup? Right, regardless of, if you did not like graphs, you could just think about this question. Okay, so what is going to happen with the image? Okay, so this is what the image looks like. That's the that is the interesting part. So the image, very interestingly, is not a semi-algebraic set. So it has infinitely many little boundary components. And in a sense, it's kind of, you can think of this as a kind of an upper boundary. On top is given by one inequality, so there is one arc. But then the lower boundary has kind of infinitely many segments, and in the end they converge, I run out of my ability to draw, infinitely small segments. But around 0, these kind of this is going to be kind of very, very, very small, very, very tiny segments. And so these red points, yes, exactly. So these red points, they look like 1 over k squared. They all lie on a nice quadratic curve. And they're images of points where all of the coordinates are equal. Finitely many coordinates are equal, then the rest are 0.
Okay, so
Yeah.
That's the union of all the images.
That's right. It's a union. So yeah. So let me describe what would happen if I just cut it at finitely many.
The nested sequence of images, how works in that?
Exactly. Let me try to draw. Unfortunately, okay, I cannot really draw it because I don't have the iPad anymore. But essentially, what would happen? I would cut it off at so they're kind of these infinitely many points. So what would happen? I would cut it at finitely many points, and I would draw kind of a nice arc from here to there. Okay, and then if I go to one more variable, I will include one more point, and then I would go like this, and then I include one more point, and I would go like this. So basically, it grows like that. Does that make sense? Did it make sense?
It makes sense. Assume that the curve is obtained just as a limit.
Yeah, so the upper curve is also obtained. That's right. The upper curve is obtained in the limit. So what happens is, another way of thinking about it is that, I don't know, for maybe, let's say, if I do it for 3 variables, I will see I will see something like this, and that. Right? I will see 3 components, right? As I add one more variable, I will see something like this. And these components, these parts will always stay as parts of the boundary as I increase n. So these parts, once they are here, they always stay as part of the boundary. But I keep on growing in this direction, and then this upper curve is only obtained in the limit. That's exactly right. Okay, any questions or concerns or answers? Comments? Anything is welcome. Okay, so now maybe you can see, you can feel, where is undecidability going to come from? It's coming from the fact that we have infinitely many inequalities, right? So you have these infinitely many inequalities. That is not so nice in some sense. And also you can see that there's already a hint of what is going to come in that, we have these really special points, and essentially these are like integer points, right? Integer points in Z. I have kind of one parameter family, and they really come, 1 over k, 1 over k squared. Essentially these are like integer points, right? So in the end, what am I going to do? So now if I have some polynomial inequality, let's say you give me a polynomial inequality in cycles that is homogeneous in the appropriate way, then essentially deciding whether this inequality is true is going to be the same as deciding whether you have some polynomial inequality that is non-negative on this contour. So let me try to, let's see what is hopefully the next slide. Yeah, so let me, so I don't know if we wrote down this theorem anywhere, but here's one way of thinking about this. So a homogeneous polynomial in even paths is non-negative if an only corresponding symmetric polynomial in P2, P4, P6, and so on is non-negative. And so what does this mean to be homogeneous? Well, you could take this as a definition, that this polynomial, the resulting polynomial, where I substitute the cycles for the sum of powers, is going to be homogeneous. Why is this? Is because, it's because of how I decided to record the ratios, right? So you can see that here I do C4 divided by C2 squared, and here I do C6 divided by C2Q, and I can also in principle do more. I can do C8 divided by the C2 to the fourth and so on. And essentially, because as somebody asked, am I going to get the same picture not only in the plane but with more? If I decided to record more of these even sums of powers or more of the even cycles, am I going to get the same image if I remember that they come as eigenvalues of adjacency matrices, and I do not? And the answer is yes, right? It doesn't matter. I can always simulate enough with eigenvalues of adjacency matrices, so the images are the same. And because the images are the same, the corresponding problems are the same. Whether you do graphs or whether you do even powers. But the important thing is that I need to decide non-negativity of this inequality regardless of the number of variables. That's the interesting part. It's not that I have a fixed, it's not that I have a fixed number of variables. In other words, you can think about it, I just have a fixed polynomial in this even power size, like P4 minus P2 squared, right? And now I say, is this no, it's not going to be non-negative, but I'm going to ask, is this non-negative for all values of n? In fact, I should do P2 squared minus P4. That is going to be non-negative, regardless of the number of variables. Okay, but that's the kind of that's the kind of question that we want to understand. Yeah.
So is it crucial that you work with densities rather than with homomorphism? Because you can...
So in some sense, homomorphism density inequalities are a special type of homomorphism number inequalities. So working with homomorphism densities is, if you want to prove that this is undecidable because it's a subclass, it's a kind of, once you prove that this class is undecidable, it will also show that the numbers are undecidable, because densities are just a subclass of number inequalities. Because I kind of I normalize by something. But here, one of the nice things about doing things through cycles, it doesn't matter. Like as I said, denominators cancel, so it didn't matter whether I record densities or whether I recorded numbers.
If you initially start working with numbers, you can draw homogeneity to that.
If I initially
This here.
no, I don't think so, because I think maybe you're right. Maybe you're right. Okay. Let's see. So there is one more thing that I wanted to mention. So I don't know if you are, hopefully you are aware, there is a very nice paper by Troilam and Resnick that looks at even symmetric sextets, right? So these are exactly polynomials in P2, P4, P6 that are homogeneous, right? But here I decided to work with, in half degree and also make the variables non-negative, right? So these are polynomials of degree 3 in P1, P2, P3 that are also homogeneous. Let's see, do I have anything that I can write this? Here. Oh, yes, there is. That's going to be sufficient. Okay, so what do these polynomials look like? You know, there is not nice choice. There is P1Q, there is P1 squared P2. So P1, P1, P2, and then there is P3, right? But because these are also homogeneous, I can divide by P. So if I divide by P1Q, right, then I'm going to kill P1Q, and here I will get P2 divided by P1 squared, and then I get P3 divided by P1Q. And you will see that these are exactly the things that I'm reporting, right? And then this guy goes into P1. And so, just to summarize the results of Chor-Lam and Resnick, they say that, you know, that basically understanding non-negativity of this polynomial, so summing times P1Q plus summing times P1, P2 plus summing times P3, you can do it by testing at finitely many points if you have finite number of variables. And you can see it exactly from this picture because, you know, a polynomial like this is exactly a linear polynomial in these variables, 1, P2, P1 squared, P3 divided by P1 cubed. So if I go to a picture like this, what does it say? That I want to optimize a linear polynomial on this contour. Right? And what happens if I optimize a linear polynomial on this contour? Well, all of these arcs are concave. So if I optimize a linear polynomial on this not contour, or on this region, then I'm going to optimize at one of the special red points. And you know, if you look at it this way, then it exactly recaptures the result of Chor-Lam and Resnick, right? But just in this limit. You could just say that it's exactly the same, or but anyway, I prefer to sort of think about this geometrically. Now that you understand this shape, optimizing a linear polynomial on this shape turns out to exactly be equivalent to optimizing the extreme points of the convex hull are basically the special red points. And that's how you get finitely many points. Okay, let me pause. Any comments? I can see that you guys are less happy with this than, than you were before. Okay, so then one of the questions that you can, one of the things that you can try to do is you can say, okay, but did it really matter that you reported only two things? So doing like P2, P3, can you do P2, P3, P4, P5, right? And more? And in principle, you know, we know how to do this for finitely many variables. And now we're kind of working on having a nice description of the limit, right? In the plane, it's kind of like everything is easy. You can draw a nice picture. But now if you start reporting more things, things become a little bit more complicated. But I think we have a good idea of what the answer is, but we still need to prove it. Yeah. Yes. That's right. So actually, that's correct. So the image is not going to be convex. So here, there is one kind of interesting thing that happens is maybe, let me mention this also. You know, so because we did things with cycles, it's natural to take power sums, right? They naturally come because of the sum of powers of eigenvalues. If you were just studying symmetric polynomials, you could say, you know, why take power sums? There are many other, you know, nice bases for symmetric polynomials. Like, why don't we record elementary symmetric polynomials instead of the power sums? And so there is actually a very nice result on the convex hull of the elementary symmetric polynomial map. So it will say, but not power. So somehow the region that you get for power sums and for elementary symmetric polynomials, if you only report the second and the third one, like P2, P3 or E2, E3, the images are basically linear transformations of each other. But if you wanted to have a more general convex hull result, then the right way to generalize it is not to take power sum polynomials, but to take elementary symmetric polynomials. Then if you take the elementary symmetric polynomials, then you will have exactly the same nice convex hull result for for regardless of how many things you record, because you will always have basically the images of these guys will always be the extreme points. So you will always have kind of a count of the many extreme points. So things will never be semi-algebraic. But if you keep recording power sums, then the corresponding result is not quite true. Then the convex hull becomes more complicated. But if you record the elementary symmetric ones, somehow you always get these arcs are going to be concave. Yeah, so the images are usually not convex, usually very far from convex. I guess that's what I wanted to do. That's what I wanted to say. Right, that's right. So the map, that's right. But here we are recording things that now, if you go to 3 quadratics, that's no, you need some conditions. And then if you go to 4, you need, I don't know if people actually know. But here we're recording things of degree 3 already, right? We're recording things of degree 2, 3, 4, and so on. Or if you want to do the squares, then we have to double the degree, right? Then you do things on the unit scale. Okay. All right. So where is undecidability going to come from? So basically, it's like I already mentioned. The issue is that somehow in this region I have these infinitely many special points. And this kind of gives me, in some sense, access to one copy of Z, right? So one copy of the integers. But so what we're going to do is we're going to do, in some sense, the same reduction as in the original paper of Khatami and Noreen. We want to deduce undecidability from knowing that deciding validity of polynomial inequalities on integers is undecidable. Right, that's basically Hilbert's tenth problem. Right. Okay, the Hilbert's tenth problem is usually stated in terms of equations, but it doesn't matter. Right. Knowing the solutions, the Diophantine equations, or knowing solutions of deciding that one polynomial inequality, it's the same because you can take sums of squares and so on. And this is known to be undecidable if you have, I think, at least 9 variables, so maybe 9 is not the right one, but there's some finitely many variables for which if you give me a polynomial with integer coefficients, then knowing whether it's non-negative on the integer points is going to be undecidable. And so what we need, but this contour that I drew for you only contains, in some sense, a copy of Z. It doesn't really give me access to Z to the K. And so what do we need to do? We need to produce independent copies of the same region. Right? If I can produce independent copies of the same region, then I will have, and I'm giving you the big picture without skipping a lot of the details. But the idea is that if I can produce the same region, if I can record, let's say, more graph densities or more graph numbers, if I produce independent copies so that my region is really just a Cartesian product of the planar region, then this will give me access to more and more copies of Z, and eventually I will end up with an undecidable problem. And so how do we do that? So here there's sort of a trick. Instead of just recording cycles, let's record these things that I call necklaces. Maybe this picture doesn't quite do justice. So the idea is, what do you do here? So instead of just gluing, so what is a cycle? You glue edges together in a cyclical fashion, right? So what is a necklace? I'm gluing triangles together in a cyclical fashion. Right? This is for the 4th cycle. Then I do the same for the 6th cycle, right? And then I can also glue together, once I do triangles, why not do the same for, complete graph on 4 vertices, right? And then glue them together in a cyclical fashion and so on. And the things that we prove is that essentially doing this gives me access to independent copies of the same region. Or we don't really necessarily need to know that it gives me access to independent copies of the same planar region, because it's enough for us to do the convex hull, and that makes things a little bit easier. We have to prove a little bit less. And then another good thing is that one of the motivation for us to do a different proof to what Khatami and Noreen did is that this proof generalizes to weighted graphs. So instead of just having edge weights 1, you can have arbitrary edge weights, including non-negative edge weights. And this is where the fact that we're doing cycles, even cycles, kind of help, because we're really recording 2 K powers, right? So the fact whether things are negative or not is not ever going to play a role. And the other good thing is that now we know that for what collections of graphs is it actually difficult to decide undecidability. So the thing about, like we just mentioned, so the thing about the original proof by Hatanya and Noreen is that they have a very delicate way of going from one copy of the bad region to many copies of the bad region, and that depends on really depends on having 0-1 edge weights. That's really kind of very combinatorial way of doing things. But here, what we do is very indelicate, right? We just build copies of the region based, we just say, okay, if we record different things, you will have access to independent copies. So that makes things much simpler and allows us to generalize things to different edge weights. Okay, but okay, so that's the first, let's say, 3/4 of my talk. And I just wanted to give you kind of a big idea of what happens and also produce this very nice planar contour and so on. Okay, let me pause and ask for questions. Yeah.
What are the polynomials of the system?
So here the idea is that basically what we prove is that if you record these things, so the idea is that basically if you try to do if you do sort of equivalent thing, then what you can show is that these guys will be sums of k, if I record these things, they will be sums of k powers of eigenvalues of a slightly different matrix, not the adjacency matrix, but matrix that counts triangles. So instead of an adjacency matrix counts kind of edges that are adjacent to the vertex. But now if you make kind of a matrix that counts triangles adjacent to the vertex and you raise it to the k power, you're going to get exactly the same thing as here. So basically what we show, is and then somehow just as before, it doesn't matter that I'm recording eigenvalues of special matrices. Right. And that gives us exactly the same planar contour that we saw before, and somehow I can also produce them independently. That's the somewhat delicate combinatorial part of this, is to say that in the end I'm recording the sum of k powers of eigenvalues of special matrices, but I can kind of take that away. Okay, so let me tell you very quickly about the sums of squares method in this thing. So first, I'm going to define a gluing algebra here. So I'm going to tell you how. So okay, if you have graphs, you can take their formal linear combinations, but you can also multiply them. But what we're going to do is I'm going to tell you how to multiply graphs with labels. So if I have a partially labeled graph, so some vertices have labels and some vertices do not, how do I multiply them? I just glue them together with the label, with the vertices that are labeled identified. So here I multiply this by this, and I just attach the one, and I get this. Now, what happens if I have an edge that's fully labeled, and I glue them together along an edge, but I don't double the edge. Right? That's the only maybe unexpected thing. This edge is not double; it just stays as a single edge. Okay, so that's my definition of gluing algebra. And now that we have these things, we can take formal linear combinations. And of course, we can do the thing that we love to do, is we can square things. Right? We can square things. So here I wrote out for you this minus this squared. So now this guy squared gives me a cherry labeled 1. This guy squared gives me a cherry labeled 2. Here, there are no common labels. So I just put them in. I just take the disjoint union. Minus 2, graph labeled 1, 2. And there's one more thing that we can do. We can take this formal expression and we can unlabel it. Right? So unlabel, and unlabeling is usually denoted by these double square brackets. So now if I take this square and I unlabel, then these two guys unlabel to the same thing, which is cherry. And this guy unlabeled gives me sort of two edges glued alongside each other. But this is the same as taking the square of an edge unlabeled edge according to my product rule, because because if things are not labeled, I just put them alongside each other, right? So basically, what this does is, if I square this thing and unlabel, I get twice Cherry minus H squared. And of course, as you can guess, what should happen if I square something? Then it should be non-negative. What should happen if I unlabel it? It should remain being non-negative. So this gives me a sum of squared proof of this inequality. Very, very simple proof. But of course, you could ask, why does this work? So I'm not going to tell you why this works. Instead, I want to give you kind of an analogy with polynomials, and then hopefully you will believe me that it works. That it works also in the graphical setup. So here is another way of thinking about polynomials. It's a very bad way, or at least it's a bad way from a point of view of drawing pictures. But let me think about polynomials as graphs where every edge only contains one vertex. So for example, here is a graph, right? So now edges only contain one vertex, right? So I drew it like this. So I have two edges containing one edge containing two, three edges containing three. This is monomial x1 squared, x2, x3 cubed. Okay. Complicated way of drawing polynomials, right? So far. So now what happens if I only partially label things, right? So what should be the meaning of something that was like an unlabeled, of an unlabeled edge containing something that's not labeled? So what this is that I take the corresponding monomial, I take the sum, and I divide by n. Right? So this guy is, I should, again, if I put two things together, I should multiply them together. But I can also go to the sum of xi j divided by n squared. And now what is the meaning of partially labeled thing? So partially labeled thing. So this, this partial label, this is x1, and this guy should give me x2 plus xn divided by n minus 1. But one of the things that's going to happen is, we're going to do some sort of a limit as n goes to infinity, right? Because we will want to evaluate things regardless of the number of variables. And then it's not going to matter whether I have this x1, an additional x1, so like x1 plus x2 plus xn divided by n. Because in the end, as n goes to infinity, the presence of this guy is is not going to affect things.
All right.
Yeah.
Xi over n, which is xi over I, or just.
Oh, no. The sum of from I equals 1 to n. So basically what I want to, just like before, I want to produce expressions that are independent of the number of variables, right? So I want to give it a meaning regardless of however many variables I have. And what happens as n goes to infinity, we get kind of a gluing algebra. Because as I mentioned before, what should be this? It's the product of xi times the product of xi divided the sum of xi divided by n times the sum of xi divided by n. So what am I going to get? Well, I'm going to get almost the sum of xi xj divided by n choose 2, but there is especially the sum of xi squared, right? Because there are still some cross products that are squares. But the cross products that are squares are going to be divided by n squared. So as n goes to infinity, these guys are going to go away. So as n goes to infinity, you kind of get a gluing algebra for graphs that contain only one vertex, where every edge only contains one vertex. And so as I mentioned before, because we know that the general problem of deciding homomorphism densities is undecidable, we know that that there should be difficult inequalities, right? Even for the sum of squares calculus, because it's going to give me a certificate of non-negativity. But one of the interesting questions is what are some interesting inequalities that we know will be hard for sums of squares? And one of the things that we can show is this very simple inequality is not a sum of squares. It's not even going to be a sum of squares of rational functions. So what does this mean? It means that I cannot multiply by a sum of squares and get a sum of squares. And even more, there is this 3 path minus h cubed even to some power that is higher than 3, which still cannot certify that it's non-negativity via sum of squares. Okay. All right, let's see, because I'm basically out of time. Let me just skip to the last slide and say and say thank you.
Thank you. Are there any questions? Other questions?
Yeah. I'm sorry? Ah, yes, that's right. So that is maybe one of the key points here. You know, one of the insights here is that, you know, why should this inequality be hard for sums of squares or even multiplying? So the thing is that, if you think about it kind of from the point of view of real algebraic geometry, if I give you a polynomial, right, then the polynomial is going to have its Newton polytope, and then you know that the sum of squares have to come from the half of the Newton polytope, right? So now if I'm going to write this thing as a sum of squares, this guy must appear from some square with positive coefficients, right? And now one of the key things is that there are not many ways of writing this guy as a square. In fact, the only way of writing this guy as a square is to fully label it. There is no other way of producing it as a square, and there is a nice characterization of going back to exactly your question of graphs that are squares. So first of all, because of the way I define Green algebra, I can always produce some graph as a square by fully labeling it, right? Because then I just attach everything to itself. But now, if I wanted to know what are things that are non-trivial squares, then you can decide whether graph is a non-trivial square. So there's kind of an interesting way of writing it as a square by knowing the automorphisms of the graph, right? So, for example, going back to this cherry, right? So the cherry is a square in an interesting way because I can write cherry as unlabeling of an edge with one edge labeled with one square like this. Okay, but this 3 path it basically has no interesting ways of writing it as a square, and that's one of the key obstructions to having a sum of squares true. No, what? Okay. Yeah. Well, so first of all, you need to decide. So first of all, let me say this: because of the undecidability result, it in some sense, nothing is going to work, right? But you can still try, but that doesn't mean that people want to give up on proving these inequalities, right? You still win. There are many different ways of doing this, not also sums of squares. But the question is, how do you now apply it? So one possibility is, of course, in some sense, is to take something that's known to be globally non-negative, or let's say non-negative for non-negative entries, and then to plug in some partially labeled graphs, and then unlabeled things. You can produce non-negative expressions in this way. And so, for example, you can do it using some of non-negative circuits or something like this. But I don't know if people understand very well what are the limits of this approach. But in principle, you could try to define some of non-negative circuits in this context also. But so far, nobody has tried doing that. So the question is how to do this properly.
I have one question about drawing graphs.
Mm-hmm.
So you said that the 8, when you take the square,
Mm-hmm.
it's the 8 itself.
Oh yeah. So
but
yeah.
why in your first example can you not glue the n-labeled 8 vertex on another 8 labeled vertex?
So the product is the definition of the product is I only glue the vertices that are labeled together.
Yeah.
Right? If they're unlabeled, I leave them alone.
Okay.
Right. So here, I'm attaching this one to this one because and here I'm attaching this to this one to this one. So in principle, there are 2 edges between 1 and 2,
Yeah.
But they are, but why don't I repeat the edge? That's what you're asking.
Yeah, no,
oh,
this,
sorry.
this I understand, but when you have the n label, this one, the n label 8, and then to square it, we say that it gives you the 8 below the thing. I know it.
No, it gives me edge squared.
8 square.
Because I just put them alongside each other, and that's like multiplying
okay.
them together. This is edge squared, not the edge alone.
Okay,
Edge squared.
sorry.
No problem. Yeah.
If positivity is somewhere important, or you just say that you not that.
Right. So, well, I guess, I mean, one way, again, I can always boil down everything to the undecidability result, right? Because deciding whether something is non-negative is undecidable. There is no way for me to do it with sum of squares. But if I add epsilon, so exactly this would give me basically strict positivity, exactly like you're asking, then it is doable. In fact, it is doable in some sense, in a not very interesting way. You could show that somehow the sum of squares certificate, if you allow yourself kind of arbitrarily sized graph, you can produce in some sense, not very interesting one. They will come from sums of squares of sort of fully labeled graphs. You're not really going to take advantage of an interesting combinatorial structure. But it is needed because otherwise, otherwise you will have undecidability and decidability kind of clashing with each other.
Okay. So, no more questions. So let's say break again.